Okay, so hi everyone. Welcome to our seventh recitation of CS 2100. And yeah, let's get it started. Um, Let me first go through a couple of announcements, and then there was a question on chat about the pigeonhole principal problem in the quiz and how to solve it. So maybe I'll quickly do that. I won't go into details, but at least I can sketch out the boxes. And then we'll solve some problems on functions and relations. So that's the plan for today. So let me just start this. And so as usual, please feel free to ask questions in chat or raise your hand and speak up, and I'll try to cover all of those. Okay, let me minimize this chat. Okay, so as usual, I have a couple of announcements first. So we are mostly done grading quiz 2. We will release the grades tonight. I want to wait a little bit and I'll talk about why on the next slide. But tomorrow morning you'll be able to see your grade. Then homework 4 will be out this Friday, October 9th. And quiz 3 is coming up. So we'll have quiz 3 on Tuesday, October 20th. And as the first two quizzes, it will be a 1 hour window between 7:30 a.m. and 4 p.m. The material that will be covered on quiz 3 will be on sets and Boolean algebra. So that's section 3 in your textbook, or lectures 8, 9, and 10. So that's the only thing that will be in the quiz. So functions and relations will be on quiz 4. Okay. So this brings me to my next really important announcement, and I posted this on Canvas as well. So I'll just go quickly over this. So basically, well, unfortunately, while grading quiz 2, we noticed a few instances of cheating for a couple of quizzes. And so so Professor Phillips and I kind of discussed how to deal with this. If you look at the syllabus, we have a strict rule that we report officially all instances of cheating, and you automatically fail the whole course if you cheated. However, after talking about it a little bit, we kind of came to the conclusion that this is, another unusual semester that is quite challenging for everyone because of COVID and teaching online and so on. And so for this quiz, we decided not to do that. And so instead of that, we offer you this one-time opportunity that if you cheated on quiz 2, you can email me, and you can find my email address on Canvas by midnight tonight. And you can just say, I cheated on the quiz, and instead of failing you the whole course, if you do that, you will just get 0 points on this quiz. So I think that's a really good and generous deal. Getting 0 on one quiz, and we do drop the lowest quiz score. So, ultimately, if you do well on other quizzes, that might not actually affect your grade, despite the fact that you cheated on this one quiz. If you don't do this by midnight, tomorrow, we will then message everyone who we found cheating and who didn't come forward. And we will go through the process for these students to fail the whole course. So that's the deal. And know that this is just an option just for quiz 2. In the future, we will not offer this. Okay, so those are my announcements. If you have any questions, do let me know. And now, let me just quickly cover this pigeonhole principle problem. So let me switch quickly to the quiz. Okay, so the problem was, and this probably was, I would say, the hardest problem in the quiz. So, if you didn't solve this, it is one of the hardest problems in addition to, I would say, proved by induction. So the problem was using the pigeonhole principle, show that for any 13 integers, there are always 2 members of the set whose sum or difference is divisible by 13. So we solved a similar problem actually during recitations or lectures. I forgot. I know we had a similar problem before. So how would you do this? You do it based on remainders. So in the first box, you put all numbers whose remainder when divided by 13 is 0. Then in the second box, you put 1 and 12, 2 and 11, 3 and 10, 4 and 9. What do we have? 5 and 8, and 6 and 7. Okay, so that's like I said, very similar to the problem we solved. And so so based now on the pigeonhole principle, if you're putting 13 integers into these boxes, there will be at least one box that will have at least 2 integers in that box. So any of these boxes will have at least 2 integers in them. And then the part that is missing, you have to then prove that if you have 2 integers in any of these boxes, that their sum or difference is divisible by 13. And so you have a couple of cases here. So first, there is the easy case. If 2 integers land in this box, the first box, then these integers are divisible by 13. And so you have something like, one of them is, I'm going to go quickly to this, just sketch it. One of them is 13 times k, the other one is 13 times l. And when you add them together, you get 13k plus 13l, and that's 13k plus l, and so on. And so it's divisible by 13. So that's the first box. If it lands into any of the other 1 to 6 boxes, then you have 2 cases. So either the remainder for both of them is k. So you have 13k plus l, and the other one is 13a plus l as well. So when you subtract them, they'll be divided by 13. Or you have 13k plus l, and the other one is 13a plus 13 minus l. And now when you add them up, you get something divisible 13. So there's a solution. And so the key point, or one kind of twist in this problem that based on Piazza discussion, some people were confused about, we have 13 integers, while the minimum number that, of integers that you need to prove this is 1, 2, 3, 4, 5, 6, 7, 8. So even if you have 8 integers, you can prove this. But you have more, right? So 13 is greater than 8. So because you have more than the minimum number required, the proof still goes through. So that's the proof. Any questions?
Yeah, there's some questions about like if 12 boxes work, and you can get it to work with 12 boxes. I'm going to post something about this when we release the grades.
Okay.
Yeah.
You can actually post it even earlier.
Okay, I'll start working on that now then.
Yeah. I haven't thought about 12 boxes, and I'm not going to do it now because in the interest of time, you have to move on. But yeah, Mark, if you could write whatever, a post on Piazza or announcement, I guess you can maybe make it work with 12 boxes, but I'm not sure how.
Yeah.
Yeah, I mean, like I said, this was the hardest problem on the exam. So yeah. Okay. So let me get back to our today's presentation. Okay, so this was the announcement. Okay, so let's do one review proof that is related to sets. So as before, we'll kind of switch between breakout rooms and me doing proofs and so on. So let's do this element-wise proof. So this is the kind of problem that will likely be in quiz 2. Sorry, quiz 3. Another note about quiz 3. Okay, so you can expect some proofs about sets. This is one kind of example of such proof. You can also expect properties about sets and so on. We did that kind of problem during the recitation on sets. Given two sets, is this true or false, and so on. So study those. Okay, so let's do this element-wise proof. So we want to prove that this union is a subset of this set on the right. So how do we prove that something is a subset? Well, if we pick an element of the set on the left, we have to show that that element is also an element of the set on the right. So in this case, let me just. So in this case, let's assume that we have some A that is an element of this union on the left. So we have x less than -3, where x is an element of R. Remember, R are real numbers. Union y greater than 3, where y is an element of R. Okay. So this is the structure of the proof. So, we assume we have such an A, and then, in the end, we have to prove that this A is also an element of this set on the right. Okay, so now by the definition of the union, we have two cases here. So if A is an element of this union, that means that A is either an element of the set on the left or A is an element on the set on the right. So we'll have two cases here. So case 1. Is when A is an element of this set on the left. So x less than -3, where x is an element of R. And so now in this case 1, we have to prove that X is an element of the set on the right. And on the next slide, I'll do this as the similar thing for case 2. Okay, so if A is an element of this set, we know that A is less than -3, and we know that A is an element of R. Okay, so so from here, we know that you know, somehow now we have to get to this form, you know, z squared is greater than 9 or a squared is greater than 9. And this is a little bit tricky in this proof. There are much easier proofs, but I wanted to do a harder one to kind of show you how we will go about this. So if a is less than -3, then we know that a minus 3 is less than 0. And we also know that a plus 3 is also less than 0. So from that, we know that a minus 3 times a plus 3 is greater than 0. So because we're multiplying two negative numbers. Okay. Okay, and now when we multiply this out, we get that a squared minus 9 is greater than 0. And from there, we get that a squared is greater than 9. And so from here, it follows that a is an element of z squared greater than 9, where z is an element of R. So this is our case 1. Any questions?
Where did you get the a minus 3 is less than 0?
So it follows from the fact that a is less than or minus 3. So if a is less than -3, then if you subtract 3 from a, it's definitely going to be less than 0. And the same thing goes for a plus 3. Okay. And where do they? Yeah, it kind of looks a little bit that it's coming out of thin air. I think I now understand the question better. It's all about looking at the goal. That's why I'm saying this is a little bit of a harder one. So your goal is to show that basically a squared is greater than 9. And you somehow have to get from, you know, a less than -3 to that. So, you know, you need some kind of square there and so on. So when I was playing with that, I kind of needed these two facts to be able to arrive there. So that's what I'm saying. So kind of, this is, I would say, the tricky step. And you kind of get there by kind of looking at the goal. So this is a little bit, this is a harder element-wise proof exactly because of this step. Usually they just kind of, this kind of falls out almost automatically. Here you have to do a little bit of thinking. Any other questions?
Yeah, someone asked if you can solve it easier if you square both sides.
Yeah, I was thinking about myself about that. I mean, I don't think the squaring both sides in general. I couldn't because these are real numbers, I think squaring both sides, I'm not sure if it preserves the inequality. So I wasn't convinced that it preserves inequality, and so I did it the other way. Yeah, actually it doesn't. Right? If you have, yeah, so squaring both sides is actually not going to work, and I can easily find a counterexample. So if you have -5 is less than -3, and now if you square both sides, you would get 25 is less than 9. So that is not true, clearly. So squaring both sides does not preserve this inequality. So you cannot just square both sides. So this actually answers your question. Any other questions? Okay. Okay, so that was case 1. Let me see what time it is. Case 2 is very similar, 11:06. So in the interest of time, I will skip case 2, and you guys should do it at home. It's almost the same as case 1. Instead of 2 negative numbers, you will have 2 positive numbers, and everything else is the same. So try to do case 2 at home. And of course, I will always post the scribbles and the solution online later if you get stuck. Okay. Okay, so this was a freshener question on sets. Let's now switch to functions and then later relations. Okay, so here's the question. So we have a set X containing elements ABC, and we define the function C, which maps elements from the power set of X into elements from the power set of sets. And the rule is that C of A is equal to X minus A. So we want to draw a 2-set arrow diagram of this function. So how do we do this? First, we have to see what our domain and codomain are. In this case, they're the same. They are the power sets of A. So let's write down all these elements. So we have empty set. That's always an element of power set of A. Then we have A, B, C. We have AB. We have AC. And then we have BC. And we have A, B, C. So that's our domain. And codomain is the same set. Oh, sorry. I wonder, it's a little button on my pen. If I press this button, is it smart enough? No, it's not. Okay. Our codomain is the same set. And sorry about my curly braces. They're kind of ugly, but you get what they are. A, B, C, A, B, A, C, B, C, A, B, C. So you can draw them either vertically or horizontally. Either way is fine. For me, this works better because of how the slides look like. Okay, so now remember, functions map each element of your domain into an element in the codomain. So let's go through all of them. So empty set. So X is ABC. So we have ABC minus empty set. So that's just ABC. So this is going to map to this one. Then we have ABC minus A. So that's BC. Then we have ABC minus B. That's AC. ABC minus C, AB. ABC minus AB, C. ABC minus AC, B. ABC minus BC is A. And ABC minus ABC is an empty set. So this is the two-set arrow diagram for this function. Any questions about this one? Okay.
Yeah.
Yes, please go ahead.
So would it be okay to reverse the order of elements in the codomain so that the arrows are easy to read?
Yeah, sure. Great question. Both domain and codomain are sets. And so the order of elements doesn't matter in either of these. I picked kind of an order that was the most natural for me to enumerate so that I don't forget an element. But you can pick whichever order you want. And you are right. If I reverse the codomain, it would look much nicer. But either solutions are correct. And in fact, you can pick any order you want. Good question. Any other questions?
What is A here?
So capital A, I guess. So it's just the definition, the rule of the function, right? So it's an argument that is passed to the function. So, we wrote it as A because we use sets here, but usually, you have something like f of x is equal to, something that mentions x, let's say x plus 2. So this is the rule for function f. So here we have this rule for function c, and this capital A here is basically the same as this x here. It's just a variable that we use to define the rule. Any other questions?
Is lowercase a an element or a set?
Lowercase a is an element of x, and uppercase A is a set. Any other questions? Okay. Okay, good. Let's move ahead then. Okay, yeah, let's do a simple proof on functions. So we have a function g that maps real numbers into real numbers. And the rule is g of x is equal to 5x minus 7. We want to prove that g is invertible by proving that it's both 1-to-1 and on-to. So if you remember from the lectures, the definition of invertible is that a function is invertible if it's both 1-to-1 and on-to. Okay, so let's do 1-to-1 first. 1-to-1 is usually a little bit easier. And we have the general structure of the 1-to-1 proof that we are going to follow. So G is 1-to-1. That's the first thing we have to prove. And the second thing we have to prove is that G is on-to. Okay, so how do we prove that G is 1 to 1? So here's the structure. So we have let x, y element of the domain be given. So that g of x is equal to g of y. So this is, this is not coming out of nowhere. This is how one-to-one proof always starts. And so this is the structure of the one-to-one proof. So we assume that we have x and y such that g of x is equal to g of y. And then from there, and using the definition of the function and so on, we have to prove that x is equal to y. And this is usually relatively straightforward. So if we know that g of x is equal to g of y, then if we plug in the rule, we know that 5x minus 7 is equal to 5y minus 7. So 7 and 7 cancel, and you get 5x is equal to 5y, and you can divide both sides by 5, and you get that x is equal to y. So that finishes our one-to-one proof. And like I said, this one is usually easier. Okay, so now we have to do the onto proof. So the structure of the onto proof that we introduced is that we assume that we are given some element y in the codomain, and then now we have to show that there is some, let's say, z such that g of z I have no idea what I just did. So the g of z is equal to y, and z has to be an element of the domain. So this is a structure, and we have to fill in the middle, right? So we are given some y in the codomain, and we have to show that for this y, there is a z in the domain such that g of z is equal to y, where z is an element of R. And so how do we pick this z? Usually you can derive z from the rule. So the rule says that g of x is equal to 5x minus 7. So we want to find z such that y is equal to 5z minus 7. And when you kind of work this out to compute what the z is, you get z is equal to y plus 7 divided by 5. So, so this is just a little side calculation to figure out what this z should be. So we continue our proof here. We take z to be equal to y plus 7 divided by 5. Now we have to show that z is an element of R. So since we picked y such that it's element of R, z is an element of R as well. So that follows form closure of plus multiplication and division. And also G of Z is equal to, we plug Z into the rule. So we get 5 times y plus 7 divided by 5 minus 7. So 5 and 5 cancel. So we get y plus 7 minus 7, which is equal to y. So, we pick some y. Then for this y, we define what the z should be. And we show that g of z is equal to y and that z is also an element of R. So we show that for any element in the codomain that we picked, there is an element in the domain that maps to it. And that finishes the onto proof. So we proved that G is both 1-to-1 and onto, and because of that, G is invertible. So this concludes the proof. Any questions about this proof?
Yeah, we have one. So I think this is on the 1-to-1. It says, does that mean that two outputs have to be the same only if the inputs are the same? Is that how we assume that it is true?
Yeah, so if you remember what 1-to-1 means, it means that if two things map to the same element in the codomain, that can happen only if these two things are the same. So that's what we are proving here. So we are picking the same element in the codomain, this x and y. So, we are assuming that they map to the same thing. And then we show that they're the same. I hope that covers it. Any other questions? I can even sketch this out. So basically, 1-to-1 means that if this is an arrow diagram, 1-to-1 means that this can never happen. So what we are proving here is that if two things are mapping to the same element in codomain, then these two things have to be equal. So you get this situation. So that is what is happening here. Any other questions?
Could you explain where the Z comes from a little more?
Yeah, in the onto proof. Okay, so yeah, the onto proof is harder than 1-to-1. So Z. So let's how to think about this. So you're given some element in the codomain, and starting from that, for that element that is given to you, you have to find some element in the domain such that this holds, such that G of Z is equal to Y. And so you can pick this Z to be whatever you want as long as G of Z is equal to Y. So you have to discover this Z on your own, so the G of Z is equal to Y. And so the way to do this is to do this little kind of side computation that I have here in this square that you use to derive this Z. So you don't have to write down this computation, actually. If you can do it, in your head, that's totally fine. You just have to pick a Z with this property. But the way you kind of derive it is by doing this little side computation in this box. So you set Y to be equal to, from the rule, you set Y to be equal to, the rule expressed in terms of Z. And from there, you divide Z. And then that's your Z that you can pick, so the G of Z is equal to Y. Okay. Any other questions? Okay.
I have one quick question. When
Yes.
you say Y is an element of OR, does that refer to the codomain?
Yeah. So here's a little bit confusing that because domain and codomain I both are.
Right.
Yeah. So this one is codomain. And this R in one-to-one proof. This R is domain. So in the one-to-one proof, you pick two elements from the domain, and then you have to show that they're equal. In onto proof, you start with an element in the codomain, and then you have to show that you can pick an element in the domain so that when you apply the function to it, you get this element. So that's a good question. Any other questions? Thanks a lot for asking questions. This is really good. Okay. If there are no other questions, and make sure to practice these proofs. They're not going to be on quiz 3, but they're going to be on quiz 4. Yes.
I don't know if these were answered. What functions aren't one-to-one or onto?
So the ones that are not invertible. I would have to think about this. So let me leave this question for Piazza or something like that. I only have 10 minutes left, and I want to solve more questions.
F of x equals x squared is 1.
Yeah,
It's
that's the
not-
one I had in mind as well.
And then is there a case where finding the inverse of G would not prove that G is onto?
Finding the inverse of G would not prove that G is onto. Yeah, so there is another way of proving that something is vertible. So you can find an inverse, and then you have to prove that when you you have to find an inverse and then to show that it is an inverse. And you show that by proving that when you compose it with the function that you get identity function. So that's another way to do it. So in the quiz, if we give a question of this type, we are going to give you a hint which type of proof to use. So here I said prove it using one-to-one and onto, but you can also prove it by discovering inverse and then showing that when you compose the function, you get identity. So that's another way of doing it. And okay, so this Mark gave a great example for a function that is not invertible. So f of x is equal to x squared. So why is it not invertible? Here is a counterexample. Because let's say both 5 and minus 5 are going to map to 25. So if you have something like this, two elements in the domain mapping to the same element in the codomain, that automatically means this is not invertible. So that's one example. Okay. Actually, so this breaks the one-to-one rule. If x is an element, if we define this function so that x is an element of z, meaning of integers, then this function is not onto either. So there will be an element in the codomain, let's say 10. And there are no elements in the domain that map to 10 because the square root of 10 is not an integer. So if you take this function f of x is equal to x squared, and you define it over integers so that it maps integers into integers, then this function is neither one-to-one nor onto. Okay, any other quick questions? So that was a great question. Okay. Let's do a simple question on relations. So we have relation R defined on set A, and it's defined by the relation less than, and we want to write R as a set of ordered pairs. So how we do this? Sorry. So R is equal to a set of order pairs. So less than. So we have to pick elements of this set A so that left is less than right. So we have 2, 3. We have 2, 4, and we have 3, 4. That was easy. Another version of this question will be draw an arrow diagram for this. So you would draw elements 2, 3, 4, and you would have 2, 3, 4, and you would have arrows from 2 to 3, 2 to 4, and 3 to 4. So this would be an arrow diagram for this relation. Any quick questions about this one? Okay, so that was the easy one. Yes.
There is no element mapping to 3, I guess.
Sorry. There is no element. What?
I think it was for the last question. Never mind.
Yeah, that was from the last one.
Okay. Yeah,
Or
there is no
for
element mapping to 3.
onto-
Sure.
yeah.
Yeah. There is no element mapping to 3 either. Okay. 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 So why don't you guys try to? I'm not going to do breakout rooms because we'll waste like a couple of minutes to put you in rooms. But I'll give you 1 minute before I solve it. So write the inverse of the previous relation. Let's say as a set of pairs. And also think about what it represents, which relation it represents. So this is so if you know the definition of an inverse of a relation, this should be really easy. So inverse boils down to, reversing the arrows in the arrow diagram or reversing each pair. So then r to the power of -1 is equal to, what do we have? 3, 2, 4, 2, and 4, 3. And to describe it in words, so R match is greater than. It matches the greater than relation, which kind of makes sense. Sorry, R to the -1 matches greater than. So if R was less than, then it kind of makes sense that R to the power -1 is greater than. Any quick questions about this? Okay. Okay, one more easy one. Why don't you try to do it on your own? So we have the relation on the set of non-negative integers. And the relation is defined by this equation. So x squared plus y squared should be 25. And we want to write R as a set of ordered pairs. Now, Note an interesting thing about this one is that both domain and codomain have an unbounded number of elements. So you can't really write down all of the elements of domain or codomain. And yet it's still really easy to write down this relation as a set of ordered pairs, because there is actually a really small number of pairs that satisfies this equation. So maybe I'll give you one more minute and then I'll do it for you. And let me know if there are any questions.
I think there's one, the last one, that says, should it not be greater than or equal?
Yeah, that's an interesting one. So that's a good question. So in this case, you are right. So greater than or equal to would work as well. So in this case, both of them would work. So I'm not really looking for, you just have to find a relation that satisfies these three pairs. So greater than or equal to would work as well. Good question. And
we have another one about how do we know when to use curly braces or parentheses?
So curly braces are used for sets, and parentheses like this are used for tuples. And pair is a tuple of two elements. So that's the distinction. And so when you have a tuple or a pair, then 3, 2 is not equal to 2, 3. So that's a great question. The order of elements matters in pairs. When you have a set, the order of elements does not matter. So this set is actually equal to this set. So that's a good question. Make sure to remember this. So that's kind of the distinction, and the distinction between these two is in the order. For tuples, pairs, and so on, the order matters. For sets, the way you list the elements in the set, the order doesn't matter. Okay, so let me quickly solve this, and then we'll stop there. So we have R is equal to a set of pairs. So what do we have? 0, 5. Related to the previous question, the order matters. So 0, 5 and 5, 0, they both have to be listed. So the first one maps 0 to 5, then the second one maps 5 to 0. We have 5, 5. No, sorry. Wrong. That adds to 50. So 5, 0, 0, 5. And then 3, 4, and 4, 3. And now I messed up the braces. This should be parentheses. Okay, so that's the answer to this question. So the order in which you list them in this set doesn't matter, but within each pair, the order matters. Any quick questions about this before we conclude? Okay. So I had one more proof about relations. So I will do this proof. I will sketch out the proof in my scribbles, and you guys can take a look at it we might also cover it during the discussions on Thursday. So thank you all for joining. And quiz 2 results are coming up soon. Thank you, everyone. Bye.